When faced with a set of parametric equations, we oftentimes like to have a visual representation of those equations, and that means we'd like to have a graph. So for this problem, we're asked to find the rectangular equation and sketch the graph. Here we have x equals the square root of t plus 4, y equals 3 times the square root of t, and t runs between 0 and 16. It's supposed to be inclusive on both of those. So when we're trying to find a rectangular equation, we use the method of eliminating the parameter, which usually boils down to trying to solve one of the equations for the parameter and then substituting back into the other equation. So here, if we take our equation x equals the square root of t plus 4, and we start to solve for t, we can subtract 4 from both sides. X minus 4 equals the square root of t, and at this point we can actually stop because the square root of t also appears in the equation for y. So we don't have to solve all the way for t every time. Sometimes we can just solve for some variation, something that includes the t. So now, in this example, we would have y equals 3 times the square root of t, but we just found that the square root of t is equal to x minus 4. So we substitute that in. Distributing the 3, we have y equals 3x minus 12. This is a line with slope 3 and y-intercept 0, negative 12. Well, this allows us to sketch a graph, and then we just have to use the information that t has, that we have for t. T runs between 0 and 16. Graph paper down here. So, again, we know that we have a line with slope 3 and y-intercept negative 12. 0, negative 12. So here's negative 11, negative 12. 0, negative 12. We know the slope is 3, so we can go up 3 to the right 1. And we'll go ahead and put some other points on here as well, just to make sure our graph is good. And this graph's pretty easy to draw anyway. 1, 2, 3, and to the right 1. 1, 2, 3, and to the right 1. 1, 2, 3, right 1. 1, 2, 3, to the right 1. A few more on here. 1, 2, 3, and to the right 1. 1, 2, 3, and to the right 1. So on. So we can then draw the line in between these points. The line probably will look better than mine. Okay. Notice that we've not given any orientation at this point to this line. The graph of a plane curve should include orientation, so we can at least remember something about the parameter. And the orientation runs from the smallest t to the largest t. So let's go ahead. We know that t, the smallest that t is 0, so when t equals 0, x is equal to the square root of 0 plus 4. The square root of 0 is 0. 0 plus 4 is 4. Y is equal to 3 times the square root of t, which in this case, again, we said t equals 0. So y is equal to 0. So when t is equal to 0, we have the point 4, 0, which is actually our x-intercept here. Okay, when t is equal to 16, this is the largest value of t for this particular problem. X is equal to the square root of t plus 4, so the square root of 16 plus 4. Square root of 16 is 4. 4 plus 4 is 8. And y is equal to 3 times the square root of t, which is 16. Square root of 16 is 4. 3 times 4 is 12. So when t is equal to 16, we have the point 8, 12. So this tells us that the portion of the graph that we're actually looking at lies between the points 4, 0 and 8, 12. And by looking at the equations for x and y, we notice that as t gets bigger, the square root of t gets bigger, plus 4 gets bigger. So as t gets bigger, x gets bigger, and the same thing for y. As t gets bigger, y gets bigger. So we know that the graph is going to run from the point 4, 0 to the point 8, 12. And in fact, that's all we need to include for the graph, because our interval for t does run strictly from 0 to 16. So this portion of the graph below the point 4, 0 can be erased, and the portion above the graph 8, 12 can be erased. So finally, we have eliminated the parameter to find our equation y equals 3x minus 12, and we have sketched the graph of this set of parametric equations, which is a line running between the point 4, 0 to 8, 12.